Hello. Continuing our series, pun intended, on the convergence of infinite series, we're going to look at another test for convergence to be able to determine if certain kinds of infinite series are in fact convergent. This test is called the integral test, and it's based on this one principle. If a function is positive and decreasing, then the series of sums to infinity underneath the curve will always be less than the integral itself. The idea here is if we start with f of 1, we go to the graph, and then we make a rectangle by going 1 unit back to 0. That creates a rectangle. We do that again for f of 2, and we do that for every function all along the way. That produces a series of rectangles whose total area can be calculated using this summation. On the other hand, the entire complete area under the curve is denoted by the integral itself. So it's clear to see that when the function is decreasing and positive, that the finite sums will always be less than the integral, and therefore we can use that comparison test concept, and that is to say, since the integral is always larger than the series, if the integral converges, then we could squeeze down and say that the series too must converge. Keep in mind, however, this condition, there's three conditions that apply here. First of all, the function needs to be positive. Second of all, the function needs to be decreasing. The third condition is the function has to be integrable. If you can't find the integral, then the integral test is not useful. So that's why we have other tests. I originally asked myself, why wouldn't we just always do the integral test for convergence? And the answer is not everything is easy to integrate. But it is an option if we see an integrable function. Like this one. When I look at 1 over n squared plus 1, first I think of different polynomial rules and power rules and so forth, but hopefully by now we've learned to recognize this as a form of the derivative of the arctangent. So I can see that this is going to easily integrate, and therefore I'm going to apply the integral test to determine the convergence of this here bad boy. Keep in mind, by the way, that in this particular series, I could use the comparison test and just compare this particular series to the series from n equals 1 to infinity of 1 over n squared. 1 over n squared, recall, is the kind of power series that we know converges, or p-series that we know converges. Later in this video, I'll prove why it works. So anyway, the integral test is not the only way to prove convergence here. This is just a demonstration of how the integral test works. So all I have to do is show that the integral here exists, it converges. By setting up the improper integral as a limit, I'm able to then anti-differentiate, evaluate from 0 to a, and then allow a to approach infinity. If we allow the arctangent of a, if we allow a to approach infinity, the arctangent is going to approach pi over 2. Remember, there's a horizontal asymptote, which is a inverse of a vertical asymptote. Since the integral converges, the series does too. So it's a really simple test if you can integrate. Now this example is going to be sort of a proof, and it's something that we're going to hopefully use throughout the remainder of this, this particular unit. And that is the idea of p-series, and when do p-series converge and when do they not. Now keep in mind here that the n is the thing that's changing over time. The power is going to be a fixed constant. So this could look at as the sum of, as n goes from 1 to infinity, of n squared, or n cubed, or n to the 3 halves. Now all three of those examples I gave you are clearly going to be divergent because it's an increasing function here. But if p happens to be a negative number, then we're going to have a decreasing function, and then we have to be a little bit more skeptical about convergence or divergence. So I'm going to start by just looking at the integral, and I had a little correction there. It was from 1 to infinity, not 0 to infinity. The idea that we're trying to do here, if p is already positive, the function increases, and therefore the integral diverges. So let's look at other situations. What about when p is negative? If p is negative, well, I still have to think about two different conditions. I have to think about when p is negative and at negative 1, but then I also have to think of when p is equal to negative 1. In other words, remember the integral of x to the negative 1 is the same as the integral of 1 over x, and the integral of 1 over x is in fact a natural log. So the functions behave differently when p equals negative 1 as opposed to any other negative p value. For any p-value not -1, we can simply reverse the power rule. So we increase the power by 1, so we have x to the p plus 1, and then we divide by that new power. So that's a review of the old antiderivative of power functions. And this then, just doing a little bit of evaluation from 1 to a. If I evaluate at 1, I get 1 over p plus 1. If I evaluate at a, I get a to the p plus 1 over p plus 1. So I take the limit as a approaches infinity of that bad boy, and notice I have common denominators here, so I get a to the p plus 1 minus 1 over p plus 1. We will note that if p happens to be between 0 and -1, then we are going to have up in here, up in the numerator, something that increases without bounds. If p is less than -1, then this whole thing is going to approach 1 over p plus 1. You might want to pause the video and think about these statements here and why I made them and how we know them to be true. I would invite you to explore the options for p-values that are between 0 and -1, and explore for p-values that are around -1, and you'll see what I mean. We still have yet... Oh, sorry. Now, if p equals -1, then the integral is going to be the natural log, and when I evaluate the natural log from 1 to a and take the limit, I'm going to get infinity. I skipped those steps here because we've seen this before, but the conclusion that I would like to make here is that the p series converges only if p is less than -1. Another way to state that is a p series written this way as 1 over n to the p only converges when p is greater than 1. So it depends on how your p series is written, whether we're talking about negative exponents or positive exponents. But either way, the understanding is if I see a series that's any sort of form of 1 over n to the 5th, or this power is anything that's bigger than 1, then I can guarantee convergence. That's a good thing. It's a nice thing for use for the comparison test, and it does make our lives a lot easier to know this. So make sure that you memorize and understand these particular facts of convergence of p series. And we'll examine that more later. One last example, and I'll go through this one really quickly. We would like to determine if the integral, and by the way, you should be careful of your boundaries. This time we're going from 2 to infinity. The reason is because the natural log of 1 is 0, and that would force us to divide by 0, and we can't do that. So we're going to go from 2 to infinity, and the question is that going to be convergent? I think I can integrate this bad boy, but the first thing I have to do is prove or verify that the function is positive and the function is decreasing. So the first thing I do at the top here is I'm saying, of course, it's positive. If we're putting in positive n values, we're going to get positive values for the natural log and for n itself. And the second thing is it decreasing? So all we have to do is show that the next consecutive term is going to be smaller than the term before it. Here again, we can see that the denominators get larger as n increases, and therefore the quotients get smaller. So I have established positivity and I've established decreasing. Therefore, the integral test is a valid approach if I can integrate. Therefore, I set up the improper integral and set it up as a limit. And this is going to be a u sub unless you can already see the connection. But I'm not going to walk you through this integration, but if you want to pause the video and watch what I did just to make sure. The bottom line here, though, is I find divergence because as I allow t to approach infinity, the natural log of t approaches infinity, and therefore the natural log of t will also approach infinity. So, in the end, we can say that this particular series diverges, not converges. So, that's how the integral test works. Thanks for watching.